Welcome to module 2.3. Now, as I said before, we are going to take a detour here and discuss about Unix user IDs and Unix processes, and then we'll go back to the confinement principle. So, what's what's an user ID, and what's the ID of the Unix processes, and all that interesting information is here. So, first of all, whenever there is a system which is based on authorization or authentication, we have this notion of subjects and principals, and this is not only in computers. You have this idea even in other places. For example, if you are going into a building which is guarded and the guard wants to see an ID, then this ID that you produce is a principal and you are the subject, and the object that you are trying to access is the building, and the guard is the authentication or authorization process that allows you in based on the principal. So, normally in the Unix, the subject is a program, because the program actually does execute on behalf of some principal. And then what is a principal in Unix? So, a principal in Unix could be actually a password and username. It could be some kind of a token, or it could be some other kinds of device which allows you to get into the system to authenticate yourself. And based on the authentication, if you go through the authentication and if you have authorization to do certain things, then you are allowed to do those things. So, an object is anything on which the subject can perform operations, and this is mediated by the rights of the subject. So, usually objects are passive things such as files, directories, memory segments, sockets, ports, and so on. But subjects can also be objects sometimes. For example, a process is normally a subject which basically accesses those objects, but sometimes we kill a process, or we suspend a process, or resume a process. So, in that case, subjects are being treated as objects. So, normally in Unix, each user ID has a unique UID, and UID 0 usually means super user or system administrator or the root. And normally a regular user or a system administrative users, they belong to multiple groups. So, and these groups might decide what kind of rights you have as a group member. And then subjects are processes, and processes normally have an UID GID pair, such as effective user ID, effective group ID, real user ID, real group ID, and saved user ID and saved group ID, and we will see what these things mean and why they are there. And so, objects are usually files or other resources. So, normally there is a one-to-many mapping from users to principals. For example, a real world user might have a passport or a driving license, or in our case Aadhaar card, some way of authenticating him or herself. So, those are all principals, and so each user might have multiple principals, but each principal has to be associated with only one user. And the reason is that otherwise, if you are going to use a principal, for example a particular password and user ID pair, and then you later on that password, user ID and password also belongs to somebody else, then how are we going to distinguish between the two users? So, obviously that won't work. And also accountability is an issue, right? So, if you have used a particular credential to authenticate yourself, then that credential better be only uniquely associated with you, so that you have accountability. So, in Unix, almost all objects are modeled as files. So, directories are files, files are arranged in a hierarchy of directories, and so on. and each object has an owner, a group associated with the object, and 12 permission bits. So, what are the 12 permission bits? So, you have the owner permission bits 3, read, write and execute, group permission bit read, write and execute, and for other or the world read, write and execute. And other than this 9, you also have what is called an SUID, SGID and sticky bit, and we will see what they are, and especially this SUID is very important in process, in Unix processes. Now, each file corresponds to an inode, and we will not go into details of inode at this point, but as you know that the inode structure basically contains information about the file and where it is actually stored in the disk, and its various meta information about the file. So, basic permission bits on a file in Unix, for example, read bit basically controls reading the content of the file, write controls the ability to write something on the file, and execute basically allows the file to be executed and loaded in memory. So, let us now just think about this. So, you can have a program either as a binary file or as a script file. So, a binary file will be executed as native code, and script file might be requiring an interpretation. So, here are some interesting questions. So, suppose a file has execute but not read permission, for let us say somebody the owner or maybe the group or for the world, then can somebody whoever has that permission, execute permission but not read, run a binary file? And the answer is no, they cannot. No, sorry, yes, yes they can, but for script file, since it is interpreted, so what will happen is that if you are to have only execute permission, then you cannot run the script file just not having the read permission. But if you have a read permission but not execute on a script file, can you execute it? And the answer is kind of yes, because you have to invoke an interpreter and then read the file into the interpreter, and then you can do that. So, for directories also these bits have importance. So, normally you do something like this, right. So, you do change mode 755 file name. So, what that gives you is that it gives you 111. So, for owner read, write, execute. 101, that means that for the group it is read and no write and execute, and same thing with the world, read, no write, execute. So, that is one way of we set the bit pattern in octal in order to change a file's permissions. Same thing can be done with the directories. Now, important thing to know here is that execution bit controls traversing the directory. So, if you want to go from one directory to its subdirectory, the subdirectory must have execution bit set in order for our if I am the owner, then the execution bit for the owner should be set. If I am part of the group, then the execution bit for the group member should be set, and so on. And so, it allows one to find the inode number from file name if the execution bit is set. And write plus execution controls creating and deleting files in the directory. So, if you do not have the write permission in the directory, you cannot delete or create new files. And then if you have a long path, then to access a file that belongs to the innermost directory, you have to have execution bit set for all intermediate directory in the path. Now, what about those 3 other bits other than those 9 bits, and that is in this table. So, SUID is basically a special bit. When set, it affects the execution of the file. For example, suppose I was discussing before that you have the change password program, say password, and this program is owned by the root, and this program is also needs access to certain resources such as slash etc slash shadow or slash etc slash password files, which are not necessarily accessible to a regular user. Now, as a regular user, you want to execute password, to change your password. So what happens then is that the root, when it installs this program called password, the binary, it sets its SUID to 1, and by changing the SUID to 1, it says that when somebody invokes this program, normally when somebody invokes a program, the corresponding process inherits the rights of or privileges of the one invoking it, but for programs which have SUID set to 1, the invocation will allow the effective user ID of that process to be that of the owner of the file, and that means the root. So therefore, even though I am calling as an underprivileged user, an unprivileged user, the password program or ping program, for example, the effective user ID is set to the owner in this case, which is the root, so that it can access those resources. So that is the use of the SUID SUID bit. So and it has no effect on non-executable files or directories. For the group ID, also the same thing, that when executing the file, it changes the effective user ID, and in case of directories, the new files that are created in the group inherits the group of the directory, and this is useful when you are doing some work as part of a group and creating new files in a directory. And in case of for the sticky bit, it is not relevant to non-executable files or executable files, but it is relevant to the directories, because if the sticky bit is set, that means that owner of a file only can delete a file in that directory. So this is what we should remember, that SUID programs or programs whose SUID is set to 1, we can do this, we can actually take the privilege level of the owner of the program file than rather than the invoking person's privileges. And the way we change this SUID is we basically do a change mode 4755 the file name, and that will set the SUID, for example, and you will see some more interesting examples later. So here some examples, like what kind of permissions are needed to read a file. F3 here, you need execute permission here, and you need a read permission here. So you can actually look into this and then look at the various interesting possibilities. Also the directory access control can also be done by program system calls from your program by many of these various library functions, which are basically wrappers. Now in Unix, while you can actually give access by changing the bit pattern of the permission bits, you cannot do a negative authorization. So you cannot say that members of a particular group are not allowed access to this file. So you cannot do that kind of a control in Unix. So other than this read, write and execute access, who can change the permission bits, right? So if I have a binary that is owned by the root and I am not a root user, I cannot change the owner from root to myself, for example. So owner has to change the permission bits, and who can change the owner? The super user or privileged users can only do that. And there are certain rights not related to a file, for example, shutting down the system, mounting a file system, listening to a low port and so on, normally reserved for root user, but the root can give that some of these privilege to other users. So now, as I said before, that each process that runs in Unix have this different IDs associated with the process. So one is called the real user ID or RUID, which is basically the ID of the owner of the process, and owner of the process is usually the one invoking the process. EUID is the effective user ID. That's actually most of the time it should be the same as RUID, but as I said, in case of SUID programs, this might be actually the owner of the file that which has been invoked to create the process. And saved user ID is used to remember in case you change the effective user ID temporarily, then you have to save the effective user ID so that you can restore it back. And this is normally needed when you are doing a privilege de-escalation followed by an privilege escalation, because once you de-escalate the privilege of your process, then you cannot re-escalate it back to a higher privilege process unless you remember, unless somehow you convince the system that you actually de-escalated. So, and we'll see that a little more, and it's the same thing about the group IDs. Now, when a process is created by fork, then it inherits all the 3 user IDs from its parent process. However, if you are doing an exec, then the SUID is checked and the SUID is set, then you basically do this effective UID and saved UID are set to the owner of the file's ID. And then during the execution of the process, you may change the user IDs via system call. And why this is needed is because there is this principle of least privilege, and the idea is that a program should be running under the least privilege that it requires. So sometimes a program might need certain privilege during the execution of the program, but there is no point in keeping escalating or heightening the privilege of the process and then keep it that way even though you do not need it, because in that case, if there is a security bug in the program, then if somebody takes control by control hijacking, then they are going to actually execute as a higher privilege user. So therefore, you want to sometimes de-escalate the privilege, but then you may need to re-escalate it again. So therefore, there are system calls which are used to do that. So then the use of ability to halt the system or bind or listen to privilege port and non-root users, as I said, that they are not modeled with this permission bits. They are usually reserved for the root user, and a non-root user might need that privilege. Then they have to escalate. Basically, they cannot do it themselves. So file level access control is not fine-grained enough in Unix, and then system integrity requires more than controlling who can write, but also how it is written. And so as I said that if you have a SUID set to 1, then they are called the set UID root programs, and they violate the least privilege principle unless programmatically also de-escalated after the need for high privilege is over, and therefore those program system calls were designed. So what one can do is that if it requires a high privilege and that is obtained by this SUID bits being set to 1 and so on, then the programmer, if he is aware of which part of the program this you need this high privilege, then after that it can drop the privilege permanently, or if a program needs high privilege at certain points of the program, not necessarily always, but in some part of the program and then later at another part of the program, then you can drop the privilege temporarily and then restore the privilege from the saved user ID that in which you saved the previous effective user ID. So, in early Unix actually they did not have the saved user ID. So, they only had the real ID and the effective UID, and they had a system call called set UID with an ID value. Now, this system call could have a different effect based on the privilege level at which the program is running. So, if the program is running with an EUID set to 0, that means the programming is running either as root or it is a set UID program, SUID set to 1 program, then set UID would set both the real user ID and the UID to the parameter. So, this is a way to de-escalate the privilege, and otherwise if you are not a privileged effective user ID, then it will only set the effective UID to the real UID. So, again it will drop privilege or keep it the same depending on what is the real UID. So, in other words, in the early Unix you could not drop the privilege temporarily, you have to do it permanently. Now, in this context I will also post this paper as study material, and you do not have to read the entire paper because it has a different purpose towards the end to do formal modeling of the this privilege changing through various system calls and so on. But you should read the first 5-6 pages to actually get a summary, good summary and comprehensive summary of what I have been talking about here in the last few slides. Now, system 5 actually added this idea of the saved user ID and a new system call. So, the system call set effective UID works if UID is 0, and then set UID could be set to any user's ID. That means that you are already privileged, so you can actually set it to another ID. Otherwise, it could set UID to UID to RUID or saved user ID. So, setting RUID temporarily drops the privilege, setting to the SUID, and so if the UID is 0, then set UID function, which is a different function, will be same as set UID. Otherwise, set UID will set all 3 user IDs to the real ID and thereby taking away the privilege. BSD also uses RUID and EUID, and and then it changes the system call from set UID to set RUID. So, here what they allow is that to swap the RUID and EUID. So, if UID is 0, then RUID and EUID could be set to any user ID, because you are privileged already, you can do whatever you want. Otherwise, either the RUID or EUID could be set to the value of the other one. So, this enables swap. That basically allows you to do a restoration of temporarily dropped privilege. So, modern Unix actually combines this idea, and it has multiple different set UID, set EUID, set RUID, and some systems also have set SREUID and so on. And this paper that I just mentioned and I will be posting actually talks about that, and then says that this semantics of this different system calls was not formalized until they did it in 2002, and therefore a lot of confusion in implementation of the system calls and also use of this system calls, and so they have done quite a bit of work there, but normally we use it very conservatively and try to understand what they mean in terms of the privilege of the program and accordingly work. So, there have been some suggested improvement in the API. So instead of calling those cryptic names like set EUID, set other IDs and so on, the method call names it has been suggested should be drop privilege temporarily, drop privilege permanently, restore privilege and so on. And that is a question of the user's mental image of his protection goals should match the mechanism. So this principle is at work with those suggestions. So now Unix file system permissions and process permissions and so on are very important in the security space. So I would suggest that you actually go through some of this material and also do some experiments on your virtual box or wherever you are doing your experimentation to figure out all the different nuances of these ideas. So that ends the module 2.3, and the next module will be about confinement techniques and more confinement techniques over what we have discussed already in the module 2.2.